Se inscreve. Oh, it's okay. You can pass it aqui. Okay. Right here, right? Yeah. Okay. Okay. So the idea is we run a crop model using high resolution regional climate models. Uh, and, the major goal was assessing the deviation of these regional climate models at target simulation performance or convection permitting resolution. Afterwards, I can explain because otherwise I'll let many lost many times. But it's not only about 4 kilometer resolution. There is some implications when you run a climate model for those resolutions. But the idea was to take the deviation of this simulation into the perspective of our model. We have five convex permitting regional climate model simulations and one base simulation that was not a power GPM, WRF, 2WF, and 3 RIGSM that it's Italy. And for evaluation that we consider the 2 crops, soybean and maize, and different sowing dates and 3 crop seasons. This is the domain of the regional climate simulation. This is here Brazil, and this is the counting that we evaluate in the simulations. It's around 2,000 count. This is the crop model. It's a new crop model that's not published yet that we are developing in Brazil. We use this model. And going to the results, basically, this is the average temperature consider the 3 crop seasons and 3 sowing dates, the average along the crop seasons. So we can see here that this is the base climate that we consider the NASA power, these the simulations. And we can see here that for temperature, the regional climate models at higher resolution does a pretty good job to simulate temperature. The average solar radiation also kind of good results also, but with more variation and some models we can see that this it's pretty small, but this is the values, and some models like overestimated the total average total radiation along the cycle. And as expected, the major problem is rainfall. This GPM rainfall, and you can see here that some models does a good job. For instance, the NCAR, WRF, and USP, that's University of São Paulo, and some this is CTP from Trieste, Italy. Some you can see clear here that it's not similar average precipitation. Okay, this is like yellow. It's between 3 and 400, and then 4, 16, and so on. So we can see here that it's pretty different pattern. And as a consequence, this the average yield. Basically, they follow majorly the same pattern, and the model that do good job simulate precipitation also has a very similar pattern of average yields. You can see here that small difference, but in general, the pattern are very, very similar. And this is some statistics. This is the temporal correlation for every counting. So basically, the blue one is between, I guess, 0.9 and 1. So very good temporal correlation. So basically, also this was the best model. And this is just an example of statistics. For instance, this model here, the CTP, have a bias of 1.58 millimeters, and these do a deviation, considerable deviation of the yield. And the opposite is not true. When the model overestimating the precipitation, then the impact is not so big because usually crop model is not so sensitive to a lot of rainfall. It's more sensitive to rainfall. So another analysis that we did, Monique, that's what we was here, did this analysis. Basically, we have many grid points, right? It's 4 kilometers and many simulations. So we try to evaluate, okay, if I just pick up 1 point, 2 point, 5, 10, 14 points, does this make any difference in the evaluation of the deviation of the models? And basically, it does, but in any case, if, for instance, if you run with just grid point, or you can see here that the general pattern between the models, you could capture as a first look. However, going to the end, although the crop simulation generally reproduce primary spatial paternity probability, some model configurations provide very low accuracy. This is very important because these models at 4 kilometers are very hard to be run. And for instance, now we want to apply for climate projections. That it means much more simulation. So basically, under the perspective of crop model, we have a group that hydrologists are the applications group. In this group, it's from the WRCP. We say that it's better to just not use this parameterization, just give up about this model, otherwise you're going to spend many resources. And even though the average evaluation, the general evaluation, you could do with a simple, just using just 1 point. The effect of the number of grid points, for instance, if you select just one single point in accounting, you could go to a deviation up to 32% for certain estimation, 21% for amazing. This is a kind of important because many users, crop models, sometimes just pick up just 1 point in accounting, or sometimes using the FAO zoning. That's worse. Then you take like 100 countings in zoning, just pick up one weather stations. And these can give you a lot of deviation, especially if you're going to use high resolution climate models. So the idea, if possible, just run more points than just 1 point. And another thing that interinstitutional collaboration, it's very important because any single institution does not have all the competence to run regional climate models, global climate models, hydrological. So to have a group working together and in a different way. Usually the PCC run the simulation, we download and you work with the simulations, but we have been working together with this group, so it's very productive when all the groups working together along the process. So thank you.
Great. Thank you so much, Santiago. Unfortunately, we don't have time for questions because we're behind. But if there's time at the end of the session and you have questions, please hold on to them. Next, we're going to move to Bruce, who is online. Bruce, I have your slides, but it might be easier if you just share from your end, but I'm also happy to share. So let me know. What do you want to do? Are you there, Bruce?
Okay. Yeah, I'm here. Got to get myself unmuted. Okay, I will try to share.
Okay, thank you.
Okay, can you all see that?
We can hear you and see the presentation.
Super. Okay. Start right into it. For several years, I was leading the Maze ET group, and we got a couple papers out on how well the different maze models could simulate evapotranspiration. But in the course of doing that, I asked a lot of the modelers to also supply their simulations of soil temperature. And in both of the sites where we were getting the ET measurements, they also had supplied soil temperatures. So I thought we should go ahead and do a test of how well those models, those maze models that did in fact simulate soil temperature, were doing on that particular job. So we've got a paper out at the beginning of the year that shows the results of that particular intercomparison. Now, oh dear, my screen is showing me sitting right in the middle of the slide in the graph, but in any event, I guess I can get through it. Okay, well, the data that we had were from Meade, Nebraska and Bushland, Texas, uh, which are both in the United States. And the Bushland measurement of evapotranspiration was from lysimeters, the gold standard, and Meade was ET, but it was eddy covariance. But that's kind of irrelevant here. In any event, there were a total of 20 different treatment years worth of data. And then when we went through all of the different simulations and tried to see how well all the different models were doing, these are the root mean square error temperatures of the different models. Now, in some cases, there are several models like SimPlace where there is more than one flavor, and MaySim more than one flavor, and then there are a whole bunch of DISSAT flavors. And then the champions of being able to do the best job were AppSim, EcoSys, Joules, and these other ones. Now, Joules, EcoSys, and AppSim are all full-blown energy balance models. Now, I don't know what you can see on your screens, but this number 12 here happened to be the DISSAT simulation, and it was pretty darn bad. And I started wondering why on earth would the DISSAT model family be so bad when that is one of the most widely used models around the world? Well, to back up from that a little bit, let me give you a little bit of soil physics of what's being used in it. First, we assume that there's an average temperature cosine wave at the soil surface. And this is an annual wave. And this is the average temperature at some depth down below, and that's the year-round temperature. And this is the amplitude of the temperature wave. And a lot of modelers take that as to being the a difference between the average temperature in, say, July minus January or something like that. This is an angular velocity. This is days during the year, the time, and this is a phase angle. Now, if you are pretty good at math, from that, if you've got a uniform soil, you can calculate the temperature at any depth, Z, and time afterwards, and it follows this equation here. And it's really a pretty cool equation, and I think. Anyway, the temperature gets exponentially decays with depth, and it gets lagged by this amount. And this D is a damping depth, which has in it the soil thermal conductivity and the heat capacity of the soil. There's a plot of the that equation that comes from Campbell 1977. So like I said, that's really a pretty cool equation. But anyway, most of the time DISAT was getting temperatures that were too high. And I started looking at the code, and here I found this equation where this is the uh, average temperature, or this is the temperature in a particular day, and then it does some averaging over 5 days. But anyway, this temperature has got solar radiation in it, and then here's 1 minus albedo, and then here's this temperature stuff. And I said, why on earth is solar radiation being used in there? If you've got a nice warm day, and you're doing an hourly kind of simulation, that makes sense. But then this is on daily time step, and every nice clear day is usually followed by a clear cold night. So what's going on? Let's just change this TMA thing to the average temperature for the particular day. And so I tried that. And lo and behold, averaged over, this is that same graph I showed you before. And instead of having this huge error, the DISAT error dropped way down to this point here, just with that simple thing. And then if you look up here, why, lo and behold, it's doing as good as Joules, which is the full-blown energy balance one. Now, this particular change has already been incorporated into the recent DISAT version 4.8.2. So if you're using that, you've got this change already in there. So that's a good news right there. But then I also was looking through the literature, and I have seen that there's some recent publications come out that for new formulations for simulating thermal conductivity of the soil. Now this is a plot of the damping depth that was in DISAT that's done with empirical equations, where this is the damping depth, and this is bulk density, and this is water content. And you can see there's a kind of a hill in it. Now, the equations that are being used in most of the models date back to about the 1960s, but this Sion model that was published in 23 has got a lot more is based on a lot more measurements of thermal conductivity, and it's pretty flat up here. It doesn't have this big hill in it. So I incorporated that into the computation of the damping depth. Then the other thing I wanted to do was to account for the difference between what the actual temperature of the soil surface is between that annual curve and what the weather is doing and what the properties of the plant crop is doing. So I did an energy balance where this is net radiation, sensible. This is evaporation from the soil surface. That is calculated in another part of DISAT, so I just grabbed that. This is transpiration from the crop surface. That too is calculated in another part of DISAT. GA is the annual temperature, the soil flux at the surface from the annual temperature wave. And then this GW is one that I've introduced, and it's the deviation between the annual temperature wave that's due to the weather and to the plant properties. Now if I were going to tell you all I did here, I'd use up all my time on that. So you trust me that I'm doing this right. Anyway, this and this have both got the calculation of what the surface temperature is in them. So I did an iteration to solve for the soil surface temperature at the surface. And then combining both the new method for getting the soil thermal conductivity, i.e. damping depth, and this method for doing the surface energy balance to get the soil temperature at the surface, and accounting for leaf area proportionate between bare soil and total full canopy. I got the root mean square error to get down to this point for DISAT. And if you go up here now, you can see I've now got it as good as EcoSys. So a lot of work here to get it a little better, but it's happened. And so, in fact, I have made some improvements in how DISAT can calculate soil temperature. Now, where do we go from here? Now, all of the measurements that I showed you were from, well, okay, I'm going to run tests over a lot more data sets. That's what I'm going to do. Anyway, the mead and bushland maize stuff is what I've shown you before. But within the DISAT package, where there's more soil temperature data on fallow, and then from mead, and there's soybean data, and Monty Salomon is going to provide some more from Kentucky on soybean. And then way back when, I did face experiments on wheat and sorghum, and I made soil temperature measurements myself. And I thought, good grief, I ought to compare them against my own measurements. So I'm going to be doing that too. And then, so the lots more running of different data sets. I'm going to incorporate a layering scheme so that the soil temperature at the bottom of one layer becomes the top of another layer, that kind of thing. And I'm also going to work on trying to account for mulches and any residue. So anyway, eventually, I hope to get a manuscript out of that, and we get this new one in as the default in DISAT. And with that, I thank you for your attention and ask if you've got any questions.
Thanks, Bruce. Unfortunately, we don't have, we're a little bit behind, so we're saving questions for the end of the session if there's some time. Thank you.
Okay.
Sue. Hold the presentation. Right here. Okay, sorry. This may look. It may not, but it may.
All right. Okay, good afternoon and thank you, everyone. I feel a bit distant from those people over there, but I don't want to be in the middle. So today I am representing the farmers from Indonesia. Maybe I don't look Indonesian, but oh, this is not on. Huh? Okay, so I'll start again. Good afternoon. I am representing the farmers from Indonesia today, and these are my colleagues from Indonesia, from Universitas Indonesian, and they are not crop modelists, they are anthropologists, so they care about what the people think and do and why. And so my plea today is about helping the farmers with the seasonal forecasts. Oh, he's working. So I thought maybe people would have already explained what seasonal forecasts are. Maybe everybody knows in the room, but it's taking something from the GCMs and taking something from the soil surface the sea surface temperatures and SOI, and being able to make some prediction for the coming 3 months and for 6 months. So this is to help the farmers in Indonesia. We were using the outputs from Australian BOM and also from IRMs. Okay. Hello? Is it okay? Oh, all right. Now it's not shouting. Sorry, they call me Walker Talker Beggar, but yeah, I wanted to be clear. Okay, so if we go to the other topic that we're looking at is the farmers' field shop. So they're called science field shops. So these are similar, probably you know about farmer field schools or climate field schools, and some of those were born in Indonesia. But the difference here is that there's a commitment from the scientists and from the extension to continually be there with the farmers on a monthly basis. So that's quite a lot of work, but it's been able to be sustained. So these science field shops started in 2008, and the only way you can belong to a farmer's rainfall measuring club is if you have a rain gauge. So this is the requirement, that you need a rain gauge. And the plots are not very big. Every farmer only has just a hectare or 2 or something like that. So sometimes the scientists say, well, why are you letting everybody measure? You know, in the climate field schools, they only have 1 measuring station for the whole village or something. But the difference here is that these farmers actually learned so much because they had their own rain gauge. And so we actually did some training of the lead farmers, and probably over 5 or 6 years, up until COVID, we trained maybe 150 lead farmers in what they call climate services. So some basics about weather and climate change, how to understand seasonal forecasts, how to do observations of rainfall, and then also some field agroecology. And this is where it's important that the farmer goes to the rain gauge every day, because these farmers actually were able to detect the pests and diseases before any of the other farmers around in their area, the ones who belong to the club. And then the other thing is that they come together once a month. So here are some of the farmers coming together, and they are then taught how to look at the dry spells or the wet spells, or when the rain is coming or not. And so these have been successful in 4 or 5 different regencies or provinces, states in Indonesia. And even in November last year, I had to do a training session for another regency online with a translator. So that's a little bit of a challenge also, because I don't speak Bahasa Indonesia, of course. So what my quest today is that there's a whole lot of farmers' data there, because for more than 10 years, sometimes 15 years, these farmers have been measuring the daily rainfall. So they can make their own probability graph. So here you can easily see this is the wet season, but you can see that there's a very big difference between some of the months. So when they get the seasonal forecast in an SMS saying it will be La Nina or El Nino or something, they go to their own data on their own farm, and they can say, oh, what is below normal and what is above normal? And so they're actually using their own information to be able to help them to make some decisions. In addition to the rainfall data, for these 10 years, they have 3 planting seasons, and they've been collecting their planting dates, their fertilizer, their yields for a number of different crops, mainly for rice, but also for maize and for some other factors as well. So there's this data and it's available. So we need some people that will help these farmers, but on condition that we're going to give us something back to the farmers. So what I do every month is I look up the seasonal forecast and say whether it's going to be La Nina or El Nino. And they send a 1-sentence SMS. This is not very good. We could actually be giving them a whole lot more, because as you heard this morning, we're talking about co-creation. We also were talking about, somebody mentioned that Indonesian rainfall season has changed. Also, the Indonesian government wants to be sure about food security. So since 2008, they've also sometimes insisted that the farmers plant 3 seasons the whole year, always with rice. And so anybody who knows about pests and diseases can imagine what that has brought on. One of these farmers from one of the rainfall measuring groups, he stood up and he went to the head of the province of the Regency and said, we're not going to plant rice in the 3rd season. And he won his case. They all planted maize in that part, and they were able to have a good season of rice the following year. Those that didn't listen to them had so many pests and diseases in the 4th season of rice. So there's quite a lot of information that's there in Indonesia. It belongs to the farmers. Even one day there was a very heavy rainfall, one of those extreme rainfalls. The National Met Service didn't have a rain gauge in that area. Well, some of them did have rain gauges, but they're underneath the trees. So they couldn't know how much rain was there. So they actually phoned up these farmers, and these farmers were so excited to see their values on the national TV. Say, this is how much rain had fallen in the area. So they're making a contribution to society. But I believe that there's another thing that we can help them with. What I want to say is that because I work with anthropologists, one of the main things that is making it successful is that there's a dynamic dialogue going on all the time. So this dialogue is then between the farmers and the extension and the scientists. And one of the climate services is called New Knowledge. So one of the times when I was there, I thought, well, I don't know what new knowledge I can bring. You know, I come from South Africa. I don't really know about rice, but I learned a lot. Anyway, I said to the people who were in the course, the participants that day, every one of you must bring some new knowledge for tomorrow. And I think 25 people brought something new they wanted to share with their colleagues, with the other farmers. We had to actually vote to see which ones we were going to do, because there wasn't enough time to give 25 new knowledges. And so you just see that their mindset has changed. So I believe that we need to have some crop modeling researchers that will really work together with these farmers, together with the anthropologists, and be able to use the rice model particularly to give them some advice on what to do. Thank you.
Thank you so much, Sue. Next, we have Monique. And your I think that's one I can share. Share.
So, hi everyone. My name is Monique. This study was developed in the context of the activities of the AgMIP group, and it results from the convergence of more than one activity of the group, and that's why it has this title, because it resulted from the convergence of the activity that is focused on writing down what are good practices for modeling yield with machine learning. And in the group, every time that I ask what we should write about. People talk about how to split the data set, but there are other issues, and one of them is the one that I'm going to be presenting. And the other activity is called CY Bench. It is a benchmark data set for crop yield estimates that was developed, organized by Dilly Paldell in our group. There will be a detailed presentation tomorrow by Pratista. And basically, it has yield for several countries over the world, provided at the administrative level that the official statistics are presented. And there are predictors associated with the yield, with the same level of the yield. This was part of the work they did. So there's NDVI and daily weather and these other features that I'm listing here. And the main goal of that activity was subnational yield forecasting. But what we did was to focus on an aspect that should also have some attention paid. That is how to design the features that are going to the yield models. In particular, we have time series of the weather, and we want to pick one value that's going to be representative of that time series. So how many values should we pick? Which periods should they represent? How do we determine which dates are going to be used as thresholds for each period? Which variables are we going to use in each period? And how we're going to aggregate them. So what happened in the past few months is that we departed from a monthly aggregation approach to one based on phenology to aggregate the time series into a few points. And when I say depart, is that because right after they compiled the data set, it was submitted to a conference and in which they had to had a benchmark performance of machine learning models. So the first models that were developed with this data set, they used monthly aggregation for the time series, for the weather time series, and so on. And what we did was to take some estimates from Wolflost that it has two periods for the development stages that are represented, and there are already estimates for thermal time for the first. This is for the first period. We took this from this research paper, and we used some of the values they determined for Wolflost and used their equations to bring that to our data set, and we could recalculate the thresholds for our data set. The only thing is that at some point we were using maize and wheat, so we did not include the vernalization and photoperiod elements of their equations, but this is easy to change since what I'm going to show now is mostly, it's just wheat. And another research paper that we used as a reference was from Dilly, who organized the dataset, and he had already faced these issues when working with machine learning for yield forecasting, large-scale yield forecasting. Basically, he used the same periods as well, but he has 5 phases because he has periods representing the transition phases. So right in the beginning of the season, in the flowering phase, between the change between the two development periods, and by the end. And as an example as well of which variables and how to aggregate the difference, how to aggregate, this is also something that appeared in his paper, that for some features, for some variables, he included maximum values, for some he used average values, and so on. So for we had different types for the aggregation. We explored using the minimum value or maximum. For precipitation, using the cumulative value is relevant. Counting of events above or below some threshold. The static features, of course, they're not relevant to this discussion. And we also added as an additional feature in some cases that are the calculated thermal time. And these appeared, and this resulted into 4 different approaches for aggregating the the time series. We have 2 periods. So we're going to take one value that's going to represent the first developmental stage and one value for the second developmental stage. We have the 5 periods from Dilly's paper. We had the default for COA bench. It included the monthly averages and also some maximum values and so on, but also some counting and the thermal time that I mentioned. And we had a simple one, just monthly aggregations of the time series and some for precipitation. So it looks, how it looks, it's a little bit like that, like this. We have the curves for minimum temperature in Germany in 2009. Each curve represents the values for one of the administrative region. And these are the purple lines represent the separations that occur for monthly aggregation. And they turn into one value that's going to, and here we have multiple values because it's each one for one administrative region, but they all happen, they represent the same period. And we see in the blue points and lines, these variability between the beginning and the end of the thresholds for aggregation. And here's one example of how the features look like. They were used for modeling with a random forest. And in fact, these average minimum temperature appeared in the rank of top features of a random forest, but I'm not going to dive into that because in the end, the results were very similar independently of the method we used, with and without feature selection. And they are often worse than using the average of the administrative region in the training set. So we're still going to improve. This is a recent project that we started. We have these next steps. Some are more machine learning related. So we can model residuals, we can distrend locations, we can discuss more how to split and evaluate our models. We can use other machine learning techniques and evaluate the fact between correlation across parameters that we use it to do a simple approach of feature selection. But we also have this aspect of aggregation that we have just started exploring, that in some cases we use the same mode of aggregation for all the features simultaneously, but in some cases it may not make sense because if you have a forecasting, the idea of the model is for forecasting. I can use an estimate of the weather and fill the missing period with forecasted weather, but it doesn't make a lot of sense to talk about that to a DBI. So another aspect is that I use the same threshold for the whole country, but even in the paper that I showed, they didn't do that. They used regions and different values for each region. So how low in the spatial aggregation does it make sense to ascribe the same thermal time to derive the thresholds? So anyone who has suggestions, we're open. AgML is open for everyone. So you're all invited. And thank you for your attention.
Thank you so much, Monique. Next is Shin. Just want to say we're probably going to run a little bit over time, but I hope everyone can stay for after Shin. There's going to be one more presentation, so please stay for that.
Last thing. Yeah.
Quickly, just want to say, Bruce, I got a message from Alex. If you can respond to his message in the Zoom chat, that would be great. Okay.
Good afternoon, everyone. I'm so glad to come here and make this presentation. My name is Xin Ge, and I come from Nanjing Agricultural University and working in France. Yeah, and my project is focused on the modeling the heat and the drought interaction effect on weight. And today I will show some result about the thermal conductance and evapotranspiration simulation results. Okay. Firstly, for the background, as everybody know, there are so many current challenge on global food security. Among them, the heat and the drought negatively affect the wheat production. And especially the heat and drought stress will infect the thermal conductance and then change the transpiration and the canopy temperature, thus affecting photosynthesis and the draw mat positioning finally to change the yield formation. So we think the thermal conductance and the transpiration is very crucial and it's basic with simulation. So our study purpose is firstly to construct a new algorithm to quantify the heat and drought interaction. And secondly, to improve the prediction of thermal conductance and the evapotranspiration using the new algorithm. Okay, so firstly, we need to get a new algorithm of the interaction factor. Here we refer to the principle of vector addition. Firstly, we need to, here we take the thermal conductance as an example. Firstly, we need to know the independent temperature and the drought temperature and drought factor about it. And then we will synthesize it using this formula to get the interaction factor HDI. And then finally, we can get the interaction value under different temperature and the soil water content. But the above algorithm that can quantify the carotene stress, because as we all know, the stress in fact will not disappear as long as stress ends. Yeah, so besides we have to quantify the accumulative effect on heat and drought. So here we set a threshold the HDI TH. And then if the HDI is less than the threshold, we think that is drought state. And then we will calculate the AHDI using this formula. So finally, we will get a FHD, and that can quantify the current and the previous stress effect. And secondly, after we get the new algorithm, we have to improve the GS and the ET model. And here we use the Jarvis JS model to simulate the thermal conductance and using a Pullman-Mondes model to simulate the ET. But both the GS and the ET model, they simulated just using the leaf parameters. But that is okay if under a normal condition. But we found under drought treatment or for the nighttime transpiration, the spike play an important role in crop transpiration. We didn't measure the exact data of spike transpiration, but we have extracted the spike temperature and the leaf temperature using from the infrared photo. And we found at night, the leaf temperature is very close to air temperature because the leaf temperature are almost close at night, but the spike temperature is significantly lower than air temperature. So we think that means at night, the spike still maintain the transpiration to heat dissipate. Yeah, so we think for the ET simulation, we have to consider, we can't overlook the contribution from spike. So we quantify the leaf thermal conductance and the spike, maybe thermal conductance, yeah, maybe from cuticular as well. We don't know that, but we quantify it respectively. So and then we use the FHD to calculate it instead of the previous independent temperature and the drought factor, and then we copy the improved GS model with PM model to simulate ET. And here have a crucial parameters is canopy resistance. So we calculate it using the JS leaf and the JS spike. And then we have conducted the weight experiment on greenhouse in China, and we set 4 temperature level and 3 water level for 5 days during exercise and the green field activity. And we test our model, and for the red line is our newest model, includes the leaf and the spikes. We found it have the high accuracy for hourly ET simulation. So the new algorithm can better simulate the hourly ET under heat and drought, we think. And for the daily ET, yeah, it's same as before. Our newest model show the highest precision as well. And besides, we also get some ET data from reference. They set different heat shock treatment and drought treatment, and besides the heat shock treatment, the heat shock during different period, and our newest model can quantify the effect. And for the drought treatment, yeah, it also can work for ET simulation. And this is some detail about our French data, and that figure is more visually to show our newest model for the last shows the highest accuracy to ET simulation. So summary it, firstly we construct a new algorithm to quantify the heat and drought interaction, and then we improve the JS model and the ET model using our new algorithm. But we know we still have a problem because we quantify it for the spike transformation just using some hypothesis. We don't have the exact data to test it. So we need to improve it in the future. And another common problem, limitation of greenhouse experiment, we need more data from field to test our model in the future. Yeah. So that's all. I haven't shown many detail about my research, but I think we can discuss later detailedly. Yeah. So thanks for your attention. Sorry. This is our campus in Nanjing Agricultural University. We welcome everybody to China, to Shanghai. Sorry, to Nanjing, Shanghai and Nanjing. Okay. Thank you.
Thank you for presentation and the invite. I have to take you up on it. Last but not least. Right.
Yeah, I think we don't really see the screen depending on the position. But anyway, I'm Rogério, and today I'm representing the with water logging team, and collaborators. So here everyone that work with us, and today I'm going to talk about the title. It's simulating with growth response to water logging. I want to start my talk by stating the obvious. Water logging is a major threat to global food production, right? And here I show a map of Europe with probability of excess of water in Europe. Whenever it's in blue here, it means there is a very high probability of heavy water excess around wind entities. So you see that many parts of France, many parts of England, many parts of Germany has problems with excess of water. And in fact, focusing France and I think it's very important to focus in France because France is the biggest wheat producer in Europe, in the European Union. Not in Europe, in European Union. And actually, the biggest declines in history of France happened in the last 10 years. which happened in 2016, and again in 2024. And in both cases was caused by excess of water. So I see I work in France, and people discuss a lot about drought and so, but the point is, those events, the point is, flooding it's more important than drought in France. And we have calculated the cause of wheat yield loss in France since 1980 until 2020 in a paper that was just published. And here we see the cause. I mean, the different colors means different different cause of wheat yield loss. I'm not going in all the crop seasons, but if you just consider the average, you see diseases are the most important factor for wheat yield loss in France. And in second comes flooding with 23% average of all wheat yield loss in France. And only fourth drought comes, and after heat. So flooding disease are very important. And in fact, those events, we in another paper, we calculated the probability of events like 2016 being the frequency of it in future, and we see that those events are probably becoming more frequent in future. So waterlogging is very important. And the thing is, what if you try to simulate 2016 using a very well-known DSAT and with crop simulation model? So here's the response. Here we have blue observed and yellow simulated, okay, in different years, and wheat yield on the y-axis. So you see 2014 simulations, observations are very similar. Same thing for 2015. If you go a little after 2018 and 19, it's 17, also okay. But then when you see 2016, we see our model that was the highest yield on average that our model simulated, right? So we simulated something close to 10 tons. If you compare to all the other years, that's the highest average. But the observations in the field were the lowest, was 5, okay? And this is because 2016 was caused by waterlogging, disease, and heavy rain, which are factors that the model doesn't consider, okay? So the model sees lots of water, usually transforms it in high yields. And in fact, we have reviewed process of 31 wheat crop models, and only 1/3 of them, they consider waterlogging effects. And it differs across this 1/3 of the crop models. It differs how they consider. Some considers impact on photosynthesis and growth, others in transpirations, others in root activities, others in visual index, and it goes like that. So what we did, our team, AgMIP10 with team, we launched last year a protocol to assess how different crop models respond to waterlogging. And that's the response. So we have here 15 crop models, and basically on the x-axis, we have the phenological stages, okay, from seedling in the beginning until grain filling. So it goes over the season. And here we have total biomass change, which means if it's 0, there is no impact of waterlogging. If it's 100, maximum impact of waterlogging. And this all simulations with 24 consecutive waterlogging. I mean, all the models were set to simulate 24 days of waterlogging in different phenological states. So we see, lots of uncertainties in different models, but in general, we can say that there are 4 main patterns of simulated growth response to waterlogging. The first one, which APSIM, for example, it's less sensible to waterlogging in the beginning, and then gets more sensible around stem elongation, 2 leaves, 3 leaves, phenological stages, and then after entasis, it's less sensible again. So there is the group 2, which is usually the model that consider direct impact of photosynthesis. And they have less impact in the beginning, but these impacts start increasing and hits the peak around the entasis, and then get less sensitive again. There is a group 3 that only consider a little bit of impact after entasis, and there is a group 4 that consider more impact in the beginning and less impact in the end. So there's lots of variation here. That's a biomass. Here is for yields. Same thing, same story. So I'm not going to details, just to say something similar. And I mean, in these 15 crop models we have that simulates impact of waterlogging, we also tested how they respond for heavy rainfall. And we did up to 1,000 millimeters of rainfall around mid-May, which in this case was just at anthesis. And what you see, that's you in sand soils, and you also force it. I mean, we create a layer that in which there was no drainage. So we assumed that if the rain was the rain was to be in there, so the drainage was zero after this layer. So always the bottom layer of the soil. So you see the sand soil, for example, in sand soil, the impact is very little, close to 10%, and in clay soil with 1,000 millimeters that you know will destroy the crop, the impact is close to 10%. And it's still, for example, for sand soils, 40% of the models they simulate no impact, it means zero. So lots of things to improve. The message I want to give is there is a major uncertainty among crop models about the impact of waterlogging on wheat growth. And to finalize, it's not just waterlogging. There are many other underestimated impacts. And here the review from, I mean, what the crop models, what type of stressors crop models considers. And you see, for example, here for wheat, and the same story for all the crops. So they do, all of them, they do drought, many of them, they do nitrogen deficit. For some new crops, many of them, they consider heat stress. But in most of the case, they don't consider waterlogging, weeds, disease, frost, pests, ozone, and other nutrient deficits. So the question is, so we use these models to predict our future of agriculture, right? So if our models cannot capture the magnitude of these impacts, how can we adapt for future climate change? So that's my message. Thank you. And that's all.
Thanks, Roger. Thanks everybody for sticking with us as we sorted through technical issues. Unfortunately, we're past time, so we won't be taking questions, but please find the presenters and I think you have not too big of a conference, so you should be able to find them and pin them into a corner and have all your questions answered. We have, I think, a reception at 6. I'm looking at Jonas.
Yeah, 6 at the guest house garden.
Okay.
And we had lunch.
Okay, at 6 there's a reception at the guest house garden, so we'll see you then. Thank you to everyone online. You might just have to email your questions to folks. So, okay, thanks everybody.
Did you try to use that?